My name is Sylvia Draper and I'm here to talk to you about doing chemistry in Trinity. And it's great to see so many of you down the science end of Trinity. That's fantastic. So, what is chemistry all about? Well, chemistry is the study of matter, and matter is anything with mass. So that includes you and me. And mass is objects have three states of matter. There is a solid, where all of the species are stuck together, holding hands as it were, and those species find it difficult to move. Basically what they can do is vibrate. And so what I've represented here with my minstrels, specially chosen, is the structure of a solid. Now, that's all the atoms holding hands and all they can do is vibrate. If we supply some energy to those, and this is my best favourite part of the whole lecture because I get to eat some of these. Everything tremendously. What happens is they take up more space. They start to let go of each other and you start to have a liquid and a liquid can flow. And if I keep eating them fast enough, I'll end up with a gas. And there'll be very few atoms, but they'll be flying around. And those are the three physical states of matter, so you can identify them. We know what's a solid and what's a liquid. I've got that. But without chemistry, you and I wouldn't be here. Every one of you is made up of solids, liquids, and gases. And some of these have very interesting properties. The problem with eating too many minstrels is that you get a bit thirsty. I need to switch off the light. Aha. Wrong one. Dark enough? Nope. Nope. This is typical scientific technique, trial and error. And some of these have really interesting properties, which means that you can have systems that look innocent enough, taste fantastic, and this material is fluorescing. What's happening here is that I'm providing the atoms in this molecule, it's quinine actually, this is tonic water, and those molecules are getting excited, and the excited light they're emitting as light. So the material is fluorescing. If we can control that fluorescence, we can make a light-emitting device. Okay. So what would happen without chemistry? Well, you and I would not be here. And worse than that, a lot of the things that have meant that modern life is as it is today would be non-existent. Let me just show you the things that chemistry touches upon. It touches upon your body. Your body is a chemical laboratory. So we make systems that can modify the behavior of your body, and if it goes wrong, we can try and correct it. We can make things that mean that our daily lives are easier. For instance, the computer screen contains in it various light-emitting materials. Without me, as a chemist, making some of those materials, you wouldn't have your watches, your mobile phones, your toothpaste, your fertilizers. None of these things would exist. So my job is to improve the materials that you use and to make them more efficient and less environmentally costly, and to make the life of everybody on this planet improved. Let me just prove to you that chemistry has been around for a very long time. In 33 BC, people started to write down chemical reactions. And that's because they realized how important it would be to reproduce the set of conditions that produced a product that had the desired properties they wanted. So these are Egyptian tombs. These are pictures from Egyptian tombs, and you can see that the colours in Egyptian tombs are entirely due to the properties of the chemicals that made them up. So the white on the background is made of magnesium calcium carbonate. Magnesium carbonate is also used as an antacid tablet, so some of you will have eaten it. The orange is arsenic and cyanide mixed together, and those two things are quite toxic, meaning that this would not be a tomb that you would enter lightly. And sure enough, you could put warnings on the walls. And the blue was the copper, the colour that indicated the kings. It represented hierarchical power, and the blue is made up from copper materials. And you can see that what you need to do is make sand and salt, heat them together, add some water, roll them into balls, heat them, you get lots of vapours, and you get a blue colour. And that blue colour was used right up into the 12th dynasty, etc., to represent the wonders of the pharaohs and kings of Egypt, all reliant on chemistry. And let me just prove to you that chemistry has been around in all societies for a very, very long time. Back in the 12th century and before, the Chinese were using various different concoctions which they found gave you different colours. Let's see what I get here. Probably won't switch on. This is not my day today. I should try it. Can you see the green in the flame? That's indicative of copper. I've mixed the copper with ethanol, and the ethanol burns just like it does on a Christmas pudding, and the salt gives you different colours of flames. That means I can make fireworks. Not only can I make fireworks, but if I can control not just the colour of the species that I make, but also the way in which it burns, this is lithium, I will be able to make gunpowder. And if I can make gunpowder, I now have a weapon. And if I have a weapon, I have a way of killing prey and making food. Okay. Roger Bacon was the first person to write down the mixture of materials that you need to make gunpowder, and he said that you need to mix potassium nitrate, sulfur and charcoal together in a particular combination, and you need to compact it, push it down the barrel of a gun. When it ignites, the gas that it produces will cause it to fly or push a pellet out of the gun and shoot somebody. Let me just show you that even without warfare, we needed chemistry. This is a guy from western Brazil. He's from the Matis tribe, and he has worked out via trial and error what poisons he should put on the end of his blowpipe. His blowpipe is very, very skillfully made. He uses the tooth of a very large rodent as a spot, so a sort of an eyepiece to look through. He uses a very small thorn which has a fault in it so that when it hits the skin of the prey, it snaps off. But the crucial ingredient that makes the animal fall out of the tree and drop down for his food is the poison. And the poison is strychnine, and it's extracted from a plant that he can find from the rainforest. He extracts it, a chemical process. He beats it, mashes it, boils it, puts it in water, concentrates it, and then uses it. And it's not the same poison for every prey, nor is it the same dose. And there is no point shooting a monkey and it running 2 miles across the rainforest roof. You're not going to run for 2 miles underneath waiting for the monkey to fall. You need the response to be very specific. Dosed, poison, specific. Now, very luckily for me, I have a fantastic helper, Noelle, who's disappeared there. But what she's done is she's put some gunpowder for me. This is the very, very concoction that Roger Bacon, and I'm going to set fire to it, and hopefully, without any dramatic effects, well, I can, I'm going to be instant. the bacons. Formation of gunpowder. Now the reason I'm hoping for no spectacular response is it's the smoke detectors and the sprinklers. So if you brought an umbrella with you, I should get it out now, just in case. So, without chemistry, mankind would still be working in the Stone Age. What got us from the Stone Age to the Bronze Age, and the Bronze Age to the Iron Age, and the Iron Age to modern Industrial Age? It was our knowledge of chemistry, how to use the natural products of our environment and turn them into something more useful. How do we create a hotter fire, something that could melt? How do we make materials that we could actually hammer into shape and make the end of an arrow? It was our knowledge of chemistry that allowed us to do that. And just to show you that strychnine has continued to be used as a poison, this is, strychnine was used to kill the Wainwrights, the poor old Wainwrights, the uncle who owned Linden House. They were all unfortunately related to Thomas Wainwright. And Thomas Wainwright was in financial difficulties and he needed to get rid of various potential wealthy heirs in the hope that he would be able to inherit. Linden House was probably his aim, and so what he did was he poisoned everybody. Mysteriously, people died. But strychnine has a horrendously bitter taste, so if you want to apply it to somebody, you need to put it in something sweet tasting that they might not notice. And so it was jelly. Arsenic is similar, and there's been very famous arsenic poisonings where the arsenic was administered in apple pies. So the next time it's a birthday party and you tuck heartily into the jelly and the apple pie, have a good look to make sure nobody else is smiling and has none. Industrial chemistry, well now the industrial age turned us from, well, what did it turn us from? It meant that we now had an energy supply, and with that energy supply we could make things in large scale. One of the most crucial chemicals, so crucial that in fact it's used as a measurement of the development of a country, is sulfuric acid. The more sulfuric acid you're making, the more developed and more industrialized your community is. And these poor ladies, notice it's the poor ladies, I suspect the men who are out killing themselves. The ladies are making sulfuric acid using metallic drums. And these metallic drums, they found, speeded up the process by which sulfuric acid was made. And that speeding up process is called catalysis, and this is a metal surface represented here by these red atoms, and these catalytic surfaces enabled the reactants and products to do their magic more quickly. In fact, catalysis comes simply from the idea that it's tapping into an affinity that is asleep. The problem with this process is that you only manage to react with the atoms on the top of your surface. So all the atoms underneath are of no use to you. And in fact, it's only 1 times 10 to the billion atoms that actually hit the reaction surface in the right place. So chemists took this idea and thought of a way in which they could speed it up. And one way to speed it up is to actually put the catalyst and the reactants together. What you do is if the catalysts are red, you bury them into solution and allow all of the surface of the catalyst to be useful. We've actually examined, using a special technique called electron microscopy, how small molecules react with surfaces, and how surfaces make the little molecules more reactive. But we go back to this. This goes from heterogeneous catalysis to homogeneous catalysis. But now we have a problem. And the new problem is that the catalyst, the product, and the reactant are all mixed up together. And we need to extract the product. We don't want the product muddled up with these other impurities. So chemists had to come up with a solution. And the solution, once you've heard it, seems really obvious. But it's this. why not attach the catalyst to a sponge, and then the reactant can flow through the sponge and create the product. So this is where technology has taken us and our knowledge of chemistry and science. Chemistry has been fundamental to all of these advancements. And the last advancement that's really kind of hitting us is the nanotechnology age, where what we want is systems as small as a molecule that can create a machine, can do what used to take a huge amount of machinery to do. So we've been able to move from vast computers to your mobile phone. We've been able to move from extraordinarily huge laboratories to reactions that can occur on a single chip on a single finger. And just to show you why chemistry is what we're going to need, not just for the past to get us where we are, but why we need it to get us where we want to be. We are going to run out of energy, and energy, you can see, has been fundamental to the reactions that we produce. And if we run out of energy, and if we run out of oil and coal, which are not renewable, we will be in huge trouble as a society. So this is something we've got to address. It's not going to happen overnight, but it's something that we need to start thinking about now. And one thing we need to think about is how to reuse materials effectively, and also to think about how to produce the chemicals we need in a more environmentally compassionate and reproducible way, without waste. And so we have people in the school here who are looking at using alternative forms of energy, using hydrogen instead of coal and oil. So for the future, what do I know? I know that you're already wearing materials that are resistant. You may have heard of glass that can self-clean. You may be wearing waxed, old days we used to wear waxed coats to keep us dry. Now you're using liquid detergents. Do you know why? You use liquid detergents because they will dissolve at a lower temperature. So your wash can be done at 30 degrees, whereas it used to be done at 60. You can add vanish. You can add a reagent specifically to target a stain so that you don't contaminate the whole of the tank, the whole of the water supply with the material. So think about chemistry. It's going to be a key ingredient to both your future and mine. And the last thing I wanted to do was I just wanted to tell you that if you've eaten your sweet already, it's too late. But if you didn't, you will notice that every sweet that you eat at Christmas that's wrapped up is actually chiral. It has a twisted, a handedness. This is my copy of DNA, and if I twist it this way, it becomes right-handed DNA. If you looked at your sweet before you ate it, you would have noticed that one end was twisted to the right, and the other way was twisted to the left. Every biological material has a handedness to it, and we have to create chemicals specifically to react with only one of the chiral molecules. So DNA, chiral reagents that react with DNA are the ones that you would use to treat cancer. But the last thing I wanted to do was I wanted to get a volunteer just to help me to try and shoot somebody in the audience. There's no point having some knowledge of chemistry if you can't. So I just wondered if there might be, could I have a volunteer? Should I have a volunteer? Okay. Oh, I'll tell you what, because you're so difficult to get out, I'll try and shoot you. Perfect. Now I just need to know where the Tesla gun is behind me. Now, I shall move my gas cylinder, because it's you I want to shoot, not me I want to disappear. And I just need some methanol. This is a little bit of methanol. Methanol is very flammable, and so if I pass an electric current through this little bit of methanol that I'm going to put in the bottom, it will cause a spark, which will make the methanol evaporate, which will cause the cork in the top of this bottle to fly out. And although I've not been known to be very accurate, I'm hopeful every year. I don't often have a volunteer, so thank you very much. I will just see. process as you use to in an engine for a model plane. Anybody fly a model plane? Okay. Best of luck then. Just in case I electrocute myself, I better just check I've done the connections correctly. Okay, here we go again. I've moved it. Sorry about that. I seem to have misfired, but there's nothing like ending with a bang. So thanks very much.